Hi and welcome to Circle Theorems. Just before we start, a reminder that there is a notes charter available for this video. Just check the description below for a download link and you can work along with me as we go through the video. So today's video is focusing on circle theorems, and circle theorems are just a collection of different rules which we can prove about the angles that are formed when we use different parts of a circle. So we're going to begin here with a radius and a tangent which are meeting at the same point. So the edge of the radius is the where the tangent touches on the circumference of the circle. And all I'm going to do is I'm just going to grab my protractor and rotate it round so that I can measure that angle, and when I line this up, we'll see here that the angle is 90 degrees. And the reason that it is 90 degrees is that there is a very simple rule about a tangent and a radius, and that is that a tangent is perpendicular to the radius. And that is very important. So anytime we see a radius and a tangent meeting, we can say that it has a 90-degree angle in between. Next, we have a shape here, which is like a delta shape. We have two lines coming from the center of the circle. So this is the center here. So two radii here, and then two more lines joining those to the circumference of the circle. And all I'm going to do here is I'm going to measure each of the angles that I can see. And so I'm going to first measure this angle, which is at the center of the circle. And so if I turn this around, I can measure this angle as, well, it looks like around 106 degrees for the inside. And so let's have a look at the angle which is at the circumference. Well, if I place my protractor again just in here and turn it round, well, I can see that the angle at the circumference is around 53. Now, what can we say about those two angles? Well, if we look at the two values, we can quickly see that the angle at the center, well, that is double the angle at the circumference. And that is our rule. The angle at the center is twice the angle at the circumference. Now, the proof of this rule actually comes from us adding one extra line in. So if we just add an extra radius here, what we've actually done is we have formed two isosceles triangles, because if we think about the fact that these are all the radius, then that means we have an isosceles triangle at the right hand side where these two angles are equal, and an isosceles triangle on the left hand side where these two angles are equal. Now, if I call this angle here x, and I call this angle y, then the angle at the centre here, well, this would be 360, take away x, take away y. That would be the size of the angle at the centre of the circle. Now, the red angles that we have marked, well, this is an isosceles triangle, and so this angle here would be 180, take away y all over 2. And the green angle, well, this would be 180, take away x all over 2. And so, if we add together the two angles, which form the angle at the circumference, well, that is going to be, this is like 90 take away x over 2, this is 90 take away y over 2, and so if I add those together, the angle at the circumference, well, that would be 180 take away x over 2, take away y over 2. And if we compare that with our blue angle, what is the relationship? Well, I multiply by 2 to turn 180 take away x over 2, take away y over 2 into 360 take away x, take away y. Next we have a circle which has been cut in half using a diameter, and then we formed a triangle within the semicircle that has been formed by cutting it in half. Now the question here is, what is the size of the angle at the circumference? Well, again, if I take my protractor and place it as accurately as I possibly can, let's turn that around. We're not quite there. There we go. What is the size? Well, that size is 90 degrees. And so we have a rule that the angle in a semicircle is 90 degrees. And the question here is, why would that be the case? Well, this, in fact, is just a very special version of the previous rule, because this is the angle at the circumference, and this is the angle at the centre. The angle at the centre is 180 degrees, and therefore the angle at the circumference must be half of that value, 90 degrees. So next we have a shape which is almost like a bow tie. We have chords drawn in different directions which all overlap in order to make these intersecting lines in the centre, forming two triangles. Now for this one, what I'm going to do is I'm going to measure each of the angles that we have on the inside here. So I'm just going to quickly rotate this around and measure that angle. If I just get that a little bit more accurate, there we go. We have 35 degrees in this section. And if I measure the same angle in this, then we turn the protractor around and we have, once again, 35 degrees. So this one and this one are both 35. And if I look at the bottom of those triangles, let's just turn that slightly. So there we have, in this case, we have 65 degrees at the bottom. And if I measure the same angle in the other triangle, so down at the bottom, well, once again, I have 65 degrees. Now, what is that telling us this time? Well, straight away we can obviously see that we have pairs of equal angles. And the reason for that, the rule that we have in this situation, is that angles subtended by the same arc are equal. Now what that means is, the word subtended just means to have straight lines at the ends. So the arcs that we are talking about, we have an arc here, and so the angles which subtend this arc are equal, the 35 degrees and the 35 degrees. The angles which subtend this arc, well, they are both equal, they are both 65. In our next diagram, we have a quadrilateral drawn inside of a circle, so all four corners of that shape are on the circumference of the circle. Now this has a special name. It is known as a cyclic quadrilateral because the four points, the four vertices of that shape are on the circumference of a circle. Now what is the rule to do with these? Well, again, all I'm going to do is I'm going to take my protractor and I'm going to measure each of the angles in that shape. And so I can see that the first angle I have is 100 degrees. And if I keep making my way around the shape, this angle is around 115 degrees. And if I keep going, then have 80 degrees, and finally the last angle, and our last one is 65 degrees. Now, if we look at these angles, this time we don't have any pairs of equal angles, so there's nothing too obvious about what we can say here. But let's look at these shapes in pairs, these angles in pairs. If I look at the angles which are opposite to each other, 180, 115 and 65. What can I say about those pairs? Well, what I can say is that opposite angles in a cyclic quadrilateral sum to 180 degrees. 100 plus 80 is 180, 115 plus 65 is 180. And obviously in total we have 360, which is the sum of the angles in any quadrilateral. So next, what we have drawn here is a triangle drawn within the on the circumference of the circle. So all three vertices are on the circumference of the circle, and then the bottom vertex of our triangle is also meeting a tangent. Now in this case this is not a radius, so we don't have our rule about a 90-degree angle. It is just a chord which the tangent is meeting in this case. So in this case I'm just going to measure the angles again. If I measure this first angle on the right hand side, I have 55 degrees, and on the left hand side I have 75 degrees. So I can mark each of those. I've got 55 degrees here, and I have 75 degrees here. And then if I look at the angles inside of the triangle, well, if I take this angle here and I rotate, just line that up a little bit better, there we go. So in there we have 55 degrees, and in the other angle, we turn this around, well, in here we have 75 degrees. And so let's mark that in. So what can we say here? Well, this time we clearly have pairs of equal angles, which is helpful. And we also have a third angle here, which actually must be the same in both cases, because one, it makes a straight line. Therefore, we should have all of these angles adding to 180. But also, if we think about the triangle, they must add to 180 as well. But the rule here is that we have angles in alternate segments are equal. Now what that is saying is that the alternate segment, when we draw a chord, we create two segments. We have the segment here, and then we have the major segment that is left. And so this segment, the 55 degrees, must match with the alternate segment up here. And the 75 degrees, here is our segment, so the alternate segment is over here, 75 degrees. And so those angles must match. And finally, what we're going to look at here is the situation where we have two tangents drawn. And those two tangents, when we draw them, they will eventually meet each other at a single point. But in this case, what we're actually looking at is not angles as such, but we are instead looking at length. What is the length of the line from the point where it meets the circumference to the point where the two tangents meet? Well, at the top here, this is 10 centimeters. And if I look at beneath that, on the other tangent, well, my distance is exactly the same. It is 10 centimeters again. And in this case, that is our rule. Tangents from a point are equal. So where we have a single point creating two tangents to the circle, that distance will be equal in both cases. And this one actually has a very obvious proof, and it is the fact that we were told they are right angles. And so if this is a right angle, what I can actually do is form myself a right angle triangle, and I can do the same to this one. And what that tells me is I have got a radius here, and I've got a radius here, and therefore this line here is the hypotenuse of each of the two triangles. And so if I know the hypotenuse and I know the radius, this extra length must be the same in both cases. They are congruent triangles. So now I just want to see if we can put together a few of these angle rules, these circle theorems, in order to find the missing angles in a diagram. And so we are first asked to find the green angle. Now the green angle is here. Now what would that relate to in terms of the diagram or the information that we already know? Well, what we need to do here is we need to think about the fact that actually this is part of a triangle, and we have a tangent with the angle marked here. Now the reason that that is important, what we've actually got here is the alternate segment theorem. And what we know about the alternate segment theorem is that alternate angles are equal, and therefore this green angle must be 60 degrees as well. This is the alternate segment to the 60 degrees. We're then asked for the pink angle. Now the pink angle is the angle at the centre of a circle, and the angle at the centre is twice the angle at the circumference, and therefore in this one we need to be thinking about the angle we have just calculated. And so this one is going to be using the rule angle at the centre twice the angle at the circumference, and therefore if this angle is 60, then the one at the centre must be 120 degrees. We're then asked to find the yellow angle. Now the yellow angle here, well, the key here is that we have an isosceles triangle. How do I know it's isosceles? Well, this is a radius and this is a radius, and therefore it must be an isosceles triangle. And so what we have is just the rule isosceles triangle. And so if this angle is 120, I'll take that away from 180, and then I will half it. So 180 take away 120 is 60 over 2, means that each angle must be 30 degrees. And then we have a final question. We want to know the size of the blue angle. So the blue angle is over here, and for this one we need to think about the fact that what we had overall was a cyclic quadrilateral, because all four corners there did hit the side of the circle. So we have the rule that opposite angles in a cyclic quadrilateral add up to 180. But that means we need to use this entire angle here. That is an entire angle of 75 degrees, and therefore the last little bit here is to do 180 take away 75, which means that the blue angle must be 105 degrees. And so we have found all of the missing angles that we were requested. And so we end with the exam question. It came from the Edexcel paper in November 2018, and it was on higher paper 1. We have our diagram here, and we are told that A, B and C are points on the circumference of a circle with centre O. DAE is the tangent to the circle at A. Angle BAE equals 56, that is this angle here. And CBO is 35. Work out the size of angle CAO. You must show all of your working. Now the very first thing I'm actually going to do here is just to mark what angle CAO actually is. So CAO is from C to A to O, and therefore the angle that I'm looking for is this one right here. Now, we're going to have to build this up. It's not going to be something that we're going to find immediately, and so what we want to do first is identify what we have within the diagram. Well, we have a tangent. If we have a tangent, that is a suggestion straight away that we want to be thinking about alternate segments or 90-degree angles. And what we have here is an angle created with a triangle. Now that is quite clearly suggesting that we have an alternate segment, and an alternate segment tells us that we have equal angles. And so what we need to say is that angle ACB equals 56 degrees, and the reason for that is the alternate segment. Now, often in exams, it's actually perfectly acceptable just to name the rule, not give the full explanation. So alternate segment there would be sufficient. So next we are why have we been given an angle of 35 degrees? Why will that help us to find any information? Well, it helps because what we've actually got here, if we add our own extra line in here, we've added an extra radius. And so what we've done is we've created two sides which are the same length in a triangle. We've got an isosceles triangle, and therefore this angle here must also be 35. But why is that important? Well, it's important because it tells me what this angle is, OCA. If the total angle was 56 and the angle that we've already marked is 35, then we are left with 21 degrees extra. Now if we have a look, what we also have is another isosceles triangle, because again we are dealing with the radius, and so the angle here must also be 21. And so what we have said there is that angle BCO equals 35 degrees, and again with this one that's because of isosceles triangle, and then also that angle CAO equals 21 degrees, and that is because of an isosceles triangle. We've used one of our circle theorems, the alternate segment, but then we've also just used the fact that we can add extra radius or radii to our diagram in order to form isosceles triangles. We have found the angle we were looking for.